Honestly, I'm still surprised sometimes how well it works and how robust it actually is. I would say do the mistakes actually. Like if you have the time, do the mistakes because you learn so much from it. Because it's like it can be a very dry topic when it comes to fluid dynamics and also very problematic to understand. But it's these videos, like a lot of people just basically understand what they are seeing, even if it's without any values or something. It's very fascinating to visualize stuff that people cannot see usually, especially with Schlieren, for example, and do some research in, let's say, bachelor's thesis or a master's thesis within 3 to 6 months, you get results. It is possible. It's not like super complicated to start with it.
All right. Lutz, welcome to my show.
Hi, how are you doing?
Good, doing fine. Today we'll talk about the fundamentals or the basics of experimental fluid mechanics. But first of all, can you tell the audience who are you in the first place and what are you actually researching?
So my name is Lutz Böhm. I'm a postdoc at the Technische Universität Berlin. So it's Technical University Berlin, but official also in English. It's the German name, so it's a mixture of it. I work in the field of transport phenomena, and especially in multiphase systems, reactive multiphase systems, and also a bit with rheology. So it's a mixture of a lot of things. And it's actually most of the stuff that I'm doing and that I'm supervising is experimental work. So I did a bit of CFD in my past, but that has been a while. So now it's mainly experimental work.
Yeah, we'll talk about maybe the differentiation between experiments and simulations during the podcast. But you work on reactive Newtonian and non-Newtonian multiphase systems. So what is that all about?
Yeah, it's kind of a mixture of a lot of different projects that I came to supervise in the end. So we had a very long-lasting project, for example, where we were looking at the mass transfer of single bubbles, for example, to liquids, and we were looking at it because in the chemical industry, it's a very interesting topic in terms of also like chemical reactions. So there's a component from the gas going into the liquid, and this component is reacting in the liquid itself. And as we know in chemical industry, not everything is behaving like water. So then we have to look at rheology, and the rheology, especially when it comes to non-Newtonian liquids, is also very much affecting, for example, the bubble shape, the rise velocity, and therefore also the mass transfer, and therefore also the chemical reaction in this case. So it's a very complex system if you look at all of it at once. So we try to separate these phenomena and try to understand everything in the end, also together, but also separate by itself.
I see. On your website, I think when you talk about bubbles rising, you also work on simulations, primarily in C++, if I'm not mistaken. Are you still doing simulations, or are you more on the experimental side of things, working together hand in hand with the simulation experts?
Yeah, actually, like my work is actually very old meanwhile, and it has not been with CCM Plus actually. It's it was the other big commercial software that we used back then. It's actually from 2009, which was my diploma thesis, and I still like those videos, so I show them still these simulations of single bubbles rising. So I worked. That's what I mean by that. I worked with CFD in the past, especially on multiphase systems again with volume of fluid method and stuff like that. There has been a project in the recent years where we also especially looked at non-Newtonian liquids and bubbles rising in it, but currently there's nothing going on actually in the field of simulations at least.
I see. When we talk about experiments, so experimental fluid mechanics, why is it so important in the first place? I mean, why would we care? We could just do a simulation and then we're pretty much good to go. Why do we need experiments?
Yeah, from my point of view, I'm not a super CFD expert, but I see it, and we have a very good expert here in the group working in that field. I think especially if we're talking about single phase simulations, there's a lot of trust, and it's earned trust that we can have in the simulations, depending on the case again, and if it's maybe gas or if it's liquid. But still, I think if you think, especially if we're talking about single phase systems, we can trust a lot of these the results that we get from the simulations. When it gets to multi-phase systems, it's getting complicated. There are different models how to incorporate this multi-phase systems into a simulation, like volume of fluid, which I just mentioned, or the other ones that are known. And there it always gets a bit problematic. Also, if you look at the results that you get, and in the end, with single phase, but I would say especially with the multi-phase simulations, you always need the validation. So nobody will, like, it's a common question that you always get on conferences when you do simulations. So how about validation? So is it true or is it not true? You will always get that question if you only do experiments. You can't avoid it. So in the end, you always need at least some kind of validation. It's not always the actual property that maybe you are interested in, but some indirect property that you have from other measurements. Let's say if you're talking about flow fields, and then you often compare this with pressure loss or something like that. So there's always this thing that you have to do basically, and to prove that you're right and that you can go further with the simulations that you do and the model that you set up, to also look at different things that are probably, and that's from my point of view, the big positive side of the simulations, that you can look at stuff that you simply cannot see in experiments.
Yeah, I think that would probably bring us to the point of intrusive versus non-intrusive experimental fluid mechanics. How do you, maybe let's start a step earlier, how do you differentiate experimental fluid mechanics to begin with? Is it 1D, 2D, 3D? Is it non-intrusive versus intrusive, or is it like, is there more to it? How do you differentiate?
Yeah, I mean, yeah, there's like a lot of things that you can talk about. You can talk about it. Does whatever you use to measure affect the flow itself? That's what you always want to avoid, but it's almost, like in a lot of cases, it's almost impossible not to somehow at least be or bring something into the liquid or into the fluid that somehow disturbs the flow. There's a question like, do you measure all the components of the flow direction, like X, Y, Z, or is it just one direction, two directions, or all three? That's one of the questions. And then, sure enough, there's always a question with the type of measurement that you're doing. Are you using and I always actually would call it a pseudo 1D measurement, because there is no actual 1D measurement. Do you use something like a planar light sheet that gives you a 2D information, or is it actually the 3D information that we are always interested in, which is almost also like, it's very hard to get this information, and we can probably say that the better it gets, the more 3D, the more 3 component, the less intrusive, the more expensive it gets, probably.
Yeah, can you name us maybe a few examples from the real world where you say a 3D fluid mechanics, experimental fluid mechanics measurement is very crucial?
Where we need it.
Where we actually need it, yeah.
Yeah, I mean, we have these, let's say, let's start the other way around. You can have very simple, let's say, tubular flows, which are laminar. So there's no problem. You need we all know basically how to calculate the velocity field. We know how it will look like. And if you have that information, you can easily, measure it with a 1D measurement technique. It's okay. And you just have to go through that field. That's okay. But if you go especially to complex geometries where a flow is going through, or where it's just overflown, and complex geometries always will have the effect of having some kind of vorticity in the system and stuff like that. Even then, going to turbulent flows, we all know that this is not a system or a flow field that is like very simple, but it's very complex, and it has all directions in it, basically. So we are working, for example, with stir tanks in our lab, and doing measurements on it. And in the stir tanks, you always have a main flow direction, and you have secondary flow directions and all these things. And to be actually able to evaluate these flow fields, you have to, you need the 3D information, at least all 3 components in one plane. That's like the least thing, like stereo PIV, for example. But ideally, you would have the whole flow field because of these different directions of main flows.
Oh, that's interesting. So when we talk about PIV, how does PIV work from its first principles?
Yeah, the basics are like in a lot of experimental measurements, fluid mechanic measurements. Basically, you put something into the liquid, some kind of particles, and then you observe these particles and the movement of the particles. That's as basic as I can explain it. In the end, it's usually like the PIV thing is actually that you have a laser which is then going through a lens, and you have a planar laser field or sheet. So you have a 2D illumination basically of the area that you want to look at, and then you have a camera perpendicular to it, and you're looking at these particles which are illuminated basically by this light sheet, and then you make two images and compare these images with a cross correlation. That's what it's called. So it's a bit of a complex mathematic algorithm that has to be used, and due to that whole thing, how it works, you can get a flow field, and like it's actually in the end it's comparable to what you get from CFD, where you have cells or basically cells that where you have for every cell one velocity vector. That's what you get from PIV as well, because you have certain so-called interrogation windows, and within each of these interrogation windows, you evaluate basically the most likely movement that the particles do in this area, which is first of all direction, and second of all the magnitude of the value.
I see. Are there different techniques when it comes to PIV? Like I guess there are several sub-branches of the PIV method, like how you do it.
Yeah, I mean, like let's start with that's going back to the two-component thing of the velocity. So if you can have a, let's say, very simple setup, which is just one laser sheet, one camera, where you get basically the two components X and Y within that shield. Then if you add a second camera and have so-called Scheimpflug adapters, which are, then you can look not with a perpendicular view on the shield, but you look with a certain angle, both cameras, and due to the, like there, it's not actually a real sheet, it's a certain thickness that the light sheet has, and you can observe with the two cameras the movement of particles within that light sheet, and then you have, but you only have the information in that light sheet, which means you have three components, X, Y, and Z, that's the direction, but only within the 2D shield or sheet that you actually illuminate with the laser. And then you can go further. It's called TomoPIV. It's a tomographic approach. And I think there are also different ways where you can use a laser to illuminate the whole volume. And I also know from colleagues from Hamburg, for example, they used a rotating mirror to move the light sheet through a volume and then take the images at different depths within the volume that they would wanted to observe, basically. So there are different approaches how to get to that 3D thing, but it's a TomoPIV approach that you can use for that.
Got it. That's super interesting. Would you say on a spectrum from like super simple experimental fluid mechanics, for example, if you use wool threads in a wind tunnel where you can basically see how the flow is behaving around a car, for example, to super complicated, where would you see PIV? Is it like super complicated? Is it more on the easy side of things? Because I feel like setting it up, I did it once in uni and I feel it's like rather complicated. It's also the algorithms, like we talked about the cross correlation. So it's a bit tricky, I guess.
Yeah, but okay, there are different, like there are even, there's something like Open PIV, for example, to evaluate the data. So there's like free software, and there's sure enough also commercial software, which is basically doing the job. So the cross correlation is not our biggest problem, to say this. If I want to, like, the point is experience in the end, I would say. It needs a lot of time and precision to set the system up properly, to put the cameras at the right position, adjust the lenses, adjust the light sheet. That takes some time usually, but if you do the measurements itself, it always depends a bit on the case, but if you do the measurements itself, honestly, I'm still surprised sometimes how well it works and how robust it actually is. So sure enough, there are different settings that you really should make sure that they are properly set. But they tell you, for example, how many particles should be within the image, and there's like a rule of thumb, and it's not always easy to match that value actually. And as I said, I'm sometimes surprised how well it works, even if you don't reach this value. Like you should always try to get it, but it works very well. So if you're asking me how easy it is, I would say if you have a bit of experience, it's an okay way of measuring. It's not super complicated from my point of view. You just need experience how to set it up properly, basically.
Yeah. With every method, there's also strengths and limitations. What would you say are the biggest strengths of PIV, and then also the limitations that come with it?
Experiments are very expensive. That's probably the first point. You know, if you want to do the very simple way of doing a planar PIV, so one camera, you're still ending up at, I don't know, nowadays maybe 70 to 100,000 to start if you take a commercial system at least. If you go to stereo PIV, the second camera, you can add, I don't know, 30,000 maybe or whatever. If you go to Tomo PIV, you go to 200,000. It gets very expensive. And the other important point from my point of view is that you can maybe make it, let's say, 1.5 times this value or 2 times the value if you're actually interested in high-speed imaging, because the systems that we are talking about or that I talked about up to here have, let's say, frequencies up to 30 hertz, maybe something like that for the frequency. It's not very high if it comes to high speed movements in liquids. So if I'm talking about the bubble, which is rising in the liquid, it's rising so fast that I can't properly actually really get the whole flow field over time.
Yeah.
I can get it at different points in time, but not the whole flow field over time, for example. So these are things that you really have to consider if you're working with that technique. And that's, I would say, like the price is probably one of the main issues that we have to think about. The other thing is that you always have to be careful with putting particles into your system. It can, like especially in multiphase systems, they can attach to the surface and they can affect how bubbles, drops, and whatever are in there, how they behave. It's definitely something that's a thing with the intrusive. It's actually non-intrusive in itself, but you have to put the particles in, and then it can be intrusive again. So, or it can change the system again. So these are probably the things that I would say are the main issues that you have to think about at this point.
Is there like a rule of thumb in terms of what kind of tracer particle material you're using for specific experiments?
Yeah, I mean, the main issue is that I think there's like a specific Stokes number that needs to be fit, which basically means that you have to make sure that the particles follow the flow. And for that, for example, they should have the same density as a liquid. Okay, that's doable. So we have two types of particles that we usually use. These are hollow glass spheres for the one case. These are like they have a density comparable to water, for example. This works very well, but still, like in most cases, especially if we go to multiphase systems, you use fluorescent particles, which have a different or which emit light at a different wavelengths. Because the main issue there is that there's a high chance that the light will be completely reflected from the surface of the bubble or the droplet, for example. And this can be an uncontrolled situation in terms of light going into the camera and destroying the camera chip. So you usually use a filter which cuts out the laser wavelengths and use fluorescent particles which emit light in the different wavelengths. So, and you only let this wavelengths through the filter into the camera. So these are the main things that we have to think about when it comes to our experiments. And actually those, like the colleagues of mine who also work single phase, they also kind of prefer the fluorescent particles. They somehow work better for them. But again, it depends a bit on the case that you're looking at.
Yeah, definitely. When it comes to, let's say I want to have my results in real time in terms of the frequency resolution, do you think PIV is one of the fastest methods, or would you say there's something maybe like hot wire anemometry where you're like even higher in terms of frequency resolution?
Yeah, definitely. So hot wire anemometry is definitely faster. So I mean, sure, it's kind of a electric measurement in the end, and this is I don't know the highest frequencies that you can go, but you can go probably definitely higher than even the fastest PIV system, I would say. So when it comes to that, it's definitely preferable. But again, with hot wire, you have to be aware that you put a wire into your liquid, into your flow, and that's definitely an intrusive system or intrusive measurement technique. But there are versions where, for example, you use a hot film, which is basically like a surface that you put on your wall of whatever is flown over or through. This would be non-intrusive, but it only gives you information at the wall, which basically means you get a velocity gradient usually. not the velocity value, which makes no sense because it's 0 at the wall. But you usually get the gradient, which is something actually I did in my PhD thesis. I didn't use hot wire or hot film anemometry. I used something called electrodiffusion method. It's basically the same principle, just with a chemical reaction, or with based on a chemical approach. And basically, it's not heat transfer what you measure, but you measure mass transfer. That's something that is comparable. And I, like myself, actually built this kind of film anode, which you put in. So it's like an electrode that you put into the wall. And I built it myself in this case. You make it flush to the wall, and then you get this velocity gradient, which we were interested in my PhD thesis, because we were interested in the shear that the flow, or the shear that acts on the wall in the flow that we were observing. And also with these hot wire anemometry, I just want to mention that they're not only 1D, but they can have 2 wires which are perpendicular to each other again, so that you can also measure the direction and the velocity and the magnitude. But again, it's intrusive, definitely, if you put it in.
Yeah, is there also like a 3-wire version? I remember I saw something like that before. I'm not sure if does it exist?
I think so. I think so. In our lab, we had the 2-wire version and calibration setup that we used for it. I'm honestly not sure, but I probably think there might be a 3-wire version. I don't know, to be honest.
Okay. When we talk about other experimental methods, laser Doppler velocimetry, for example, or others like Schlieren method, for example, what are some of your favorites that you can talk about in this podcast?
Yeah, unfortunately, I missed the laser Doppler time at our department here. So we had it in the past, but I think like 5 or maybe 5 years before I even started working here, they somehow stopped working on it. But actually, in the past, we had collaborations with, it's called the German National Metrology Institute, which is sitting here in Berlin and in Braunschweig. And they were doing a lot of stuff in laser Doppler velocimetry, like ultra precise measurements. It's crazy the effort that they put in, because they wanted to use it to calibrate basically flow meters. And it's crazy what they did there. It's really interesting PhD thesis that you can find on the work that they did there. But when it comes to my favorites, it's definitely one of my favorites is definitely Schlieren, because I started that thing here at the department. So I, like in the past, at some point I saw some video on, I don't know, maybe back then even at Facebook or whatever it was. And I was fascinated by it. And I, like at some point, a PhD student came to me and he had a certain like problem. And I was asking, like, maybe you can try Schlieren and like go down to the basement. I think we have a lot of lenses there, and maybe check if you can set up a system and maybe use it. And he put a lot of effort in it, and he did a really great job. And then we started this whole thing with Schlieren here at the department. Again, we are here more interested in looking at mass transfer with the Schlieren measurement technique. But I think all the videos that you find online especially are like showing a lot of, let's say, flows from, I don't know, if you cough, for example, that's some of the things that you find. And also, like one of your former guests, he works a lot with Schlieren when it comes to ultrasound and these things. That's great to visualize. In the end, it's always a question, can you actually measure or like evaluate values, velocity values with it? That's one of the points when it comes to qualitative or quantitative measurement methods. Schlieren is definitely one of the things where when it comes to flow, you can visualize it, and it's always great for presentations and to get an understanding of what's happening. When it comes to values, it's a bit more problematic, I would say, especially like velocity values. Like mass transfer, we can evaluate concentrations with it. Or temperatures for sure. But when it comes to velocity values, I'm actually not even sure if it's possible to do that with Schlieren.
Yeah. I was wondering, what are some of the things we have to take care of when we're experimentalists and performing experiments? Like what are the things that could go wrong potentially?
Yeah, that depends a lot on the measurement technique. For example, one of the things that we didn't talk about yet is I said that we have not real 1D measurements. For example, you always have to be aware that there's a trade-off usually between the volume that is actually evaluated when it comes to 1D measurement, and the time or the frequency that you can measure. So it's you talk about voxels in this case, for example, and there's always this trade-off. You can either have a larger volume and higher frequency, or you can have a low frequency at a smaller volume of this voxel, for example, to actually have a 1D value. These are things that you definitely have to consider. And in the end, it always depends on the case that you have. Is it a high frequency case? Then you really have to think about if you're using, for example, a 15 or 30 hertz PIV measurement method. How big is the area that you're actually looking at? Is the overall flow in a, cubic meter range? Then it's probably not so bad to have a hot wire in there. It won't affect the overall flow too much. But if you're looking at very small volumes and flow that goes through that volume, you will affect it a lot. So it really depends on the cases that you're looking at, how important it is, or how important it is to look at different of these aspects, for example.
Yeah, I would be interested. Let's say someone wants to become an experimentalist, or maybe is a student working on a thesis. What are some of the mistakes that you have done in the beginning where you look back and say, oh, that was so stupid, I could have avoided that mistake? Just maybe as a tip, maybe your top tips to experimentalists out there.
I would say do the mistakes, actually. Like if you have the time, do the mistakes, because you learn so much from it. I remember the first time I worked with the PIV. So actually I also was the one at the department who was the first one we bought the system based on I had no idea what to do with it actually. And back then, because we were no experts here, we bought it and we started working on it. And I remember the first day and we didn't get any images of particles. No way. We spent the whole day and at some point we were not sure if we should call the company and ask what can we do. And then at some point you realize, okay, you put the wrong filter on the lens, which cuts out the light. So obviously you cannot see anything from the particles. You do these stupid mistakes, but be sure I never did this mistake ever again. Whenever I hear stuff like that from students, that's the first go-to point where I say, okay, please check the filters. So, and then it also comes to evaluation, especially. You can set up the system and you always have to be sure that everything is set up properly, but you get a bit of experience and that's okay. You don't, you can do mistakes, but it's okay on this side. At some point, you realize that you actually have to analyze all the data that you recorded and all the images. And there you really have to be careful what you do, especially when it comes to PIV, for example. Again, you can do this cross correlation and the code is doing it for you. Yeah. You still should get an idea what it's doing, because it actually, as I mentioned earlier, it actually gives you the highest probability of a direction and value at a certain point. And if you understand this, you can actually also realize that if you have reflections, like very bright areas within the image, this can pretty much ruin your whole measurement within a certain area. And this is stuff that you really have to think about when you use these optical measurements to make a preparation, pre-processing, I would call it, although it's experimental work, is really, really crucial. And if you don't take care that your images are well, you will not be able in the end to correct this with the actual image that you analyze. So I would say the whole process of setting up the system is very important to also make a proper analysis in the end, and especially when it comes to the analysis, there are different things that you can do, and you shouldn't probably do all the stuff that is possible. Stay to the stuff that you actually understand that you're doing.
Yeah, for example, when you set up a Schlieren system, which is pretty easy to set up, for example, at home, how do you, if you make a mistake in terms of measuring, like some weird values come out at the end, you're using a specific algorithm and then you see the values don't make any sense. How do you track down a mistake of the experiment? How do you do that?
Yeah, I can give you a very sophisticated way, which a PhD student of mine just basically did his whole PhD thesis on. So what he did, he used a colleague of mine. Okay, let's start with the beginning. So let's do the setup. The setup that we were looking at was a sphere, and there was heat transfer from the sphere to the liquid. Mm-hmm. It was basically a free convection case, so there was no flow. One colleague of mine did a CFD simulation to actually calculate the temperature field around that sphere. Then the other PhD student used that CFD temperature field, put it into COMSOL, And in COMSOL, they can do light ray tracking. And we can actually evaluate how those light rays will be affected by the temperature field and by the temperature gradients that are in there, which is the basic thing that Schlieren is doing, evaluating. Mm-hmm. And then he took the results that he would get from the light ray tracing. At some point there was a virtual chip, and he got this result from the virtual chip, and he took this result from the virtual chip in COMSOL and used his algorithm to calculate back again the temperature field. And he wanted to understand if he gets the same temperature field like the one that we put into the CFD simulation, and that we got from the CFD simulation. I'm not sure if you can get it, but it's very complicated way doing CFD, put in COMSOL, doing light tracking, having a virtual chip, and on the virtual chip he actually uses this data to evaluate his algorithm, which is very complicated for Schlieren if you want to evaluate this temperature field, to actually check if his algorithm is working properly, for example. Yeah, so it's a very, you can make it very complex if you think about certain cases, and that's what he did. But his main issue is the algorithm that I wrote to evaluate the temperature field around the sphere. Is it actually working? Does it give me proper values? And that's what he was able to prove that it's working, which was good for him. But it was a lot of effort actually to prove that his algorithm actually worked with CFD, COMSOL, all these things,
Yeah. Before you start from scratch yourself, how do you approach, for example, you want to test something in the lab? How do you look for papers, for example, specific books, specific literature to make sure you're either avoiding mistakes or you learn from someone who already has done the mistakes themselves inside of papers?
Yeah. I'm not sure how your experience is, but people don't talk about mistakes in papers. That's a bit of a problem.
That's true.
Yeah. It's pretty sad actually, because sometimes rarely you find papers where they actually tell you all the stuff that didn't work, and that's super helpful from my experience. But a lot of people don't talk about too much. And I know it from myself. It's not like something that you really want to talk about. You want to talk about the success and the beautiful images that you record. But sure enough, if you're talking about, let's say, stir tanks, that's something that we're doing a lot, and we're looking a lot at stir tanks, flow fields in there, and so on. There's a lot of literature that you can find and a lot of people talking about certain things. But in the end, you always realize the specific thing that you are interested in is very often has not been done before, or has not been observed before. So you always, in the end, you have to go into what has been done, sure enough, and maybe see how they have done it. But in a lot of cases, because you have a certain issue that you want to solve, you have to go into it yourself, basically, to see how to get to the value that you want to have in the end.
Yeah. What literature, when we talk about literature in our papers, what literature or books do you personally recommend for students, for example, writing their bachelor, master thesis, maybe even PhD thesis on experimental fluid mechanics?
So the one book that is really very comprehensive when it comes to all different, a lot of different ways. It's been I think it's 10 years old or something, or maybe even more. It's from Tropea. I think it's called Experimental Fluid Dynamics.
It's a thick one, right? A thick red one.
It's a pretty big book because it covers so many things, like basics in fluid dynamics first of all, but then goes into a lot of different measurement techniques and is talking about a lot of these issues that I also talked about, like having 1D, 2D and 3D measurements, or having the different numbers of components, X, Y, Z, and all these things. And is it intrusive? Is it non-intrusive? Yeah. A lot of these issues are covered within that book, and it's very comprehensive. I liked it a lot when I read it. And I think if you want to have a start in experimental fluid dynamics, that's the go-to book, I would say.
Definitely. I also use it to prep for my exam. So definitely. I would also recommend it. We have to talk about machine learning and AI. How is it used at the moment in experimental fluid mechanics? And if it's not used, where do you see the future heading towards in terms of how experimentalists will use AI or other emerging technologies to learn more from the flows, whether it's turbulent flows or laminar flows?
Yeah, the question is always in the end, we're talking about statistics, right? ML and all these, AI is basically statistics. That's what, if you talk to mathematicians, they always tell you, that's what it is in the end. That doesn't make it bad. I just want to mention that this is basically the starting point when it comes to this field. To my experience, I think this is nothing that has been incorporated, for example, in measurement or in the evaluation softwares when it comes to PIV, for example. But I can imagine having it in a certain or having it incorporated in a certain way when it comes to prediction of other conditions. For example, if you measured a certain condition and maybe with AI, it's possible to say, okay, if I change, I don't know, the viscosity, how will this affect the flow, for example? I can imagine that this is going in this direction, but in the end, that's the same probably that is going on in the CFD field, which like it's something that is fairly new to my experience when it comes to these evaluations of fluid dynamics. And it's not widely used yet. I know areas also in process engineering, where I'm coming from, where we start using it, especially in image analysis tools. But for the fluid dynamics, I guess it will go in the direction of prediction, and that's the area where it has the most potential, probably. Although you always have to be a bit careful about prediction of stuff that has not been measured.
Definitely. So this was just an intro to experimental fluid mechanics. Of course, if people want to learn more from Lutz, please write it in the comments or tweet to us if you want to, because Lutz is also very active on Twitter, probably more than I am. And then, follow him there as well. Any closing remarks from your end, Lutz? Any recommendations, last words, motivating words to all the experimentalists out there?
The thing is with fluid dynamics is it's the same with CFD actually, but also with experimental fluid dynamics. You can always fascinate people with it. So in the past, I shared a lot of videos and images that we recorded in our lab, and it's always fascinating. It's not only for like doing maybe a bit of science communication, but also for scientific presentations on conferences. You can always show a graph and have a line going somewhere, but people will always remember the image, the colorful images. And experimental fluid dynamics has a lot of potential of giving you very nice videos and images that maybe give the audience the possibility to grasp more what's going on. Because it's like it can be a very dry topic when it comes to fluid dynamics, and also very problematic to understand. But it's these videos, like a lot of people just basically understand what they are seeing, even if it's without any values or something. It's very fascinating to visualize stuff that people cannot see usually, especially with Schlieren, for example. It helps a lot to understand what's actually going on. And even if you don't even give numbers in the end, people will understand it more and will be fascinated more by it. I just want to mention, especially when it also comes to experimental fluid dynamics, it is possible to get into basics and do some research in, let's say, bachelor's thesis or a master's thesis within 3 to 6 months. You get results. It is possible. It's not like super complicated to start with it. It can get super complicated depending on the case that you're looking at and all the stuff that you want to evaluate. But it's not witchcraft. It's basic physics, basically what's happening, and mathematics. You always have to think about the right technique, but in the end, you will be able to start with it fairly quickly and get results also fairly quickly. But at some point, you probably your desire to get more into it will start, and that's a point where it's getting really interesting, and where you really start thinking more and trying to squeeze everything out of it that you can. And that can, like, especially in the work that we are doing here, we are always at the edge of stuff that is possible. And that's really interesting at the university level, basically. I think in industry, they are doing, let's say, basic stuff that works. But we are really trying to always get to the edge of what's possible. And then you have to think about new solutions. And I think that's always very interesting.
I think if that's not motivating, then I don't know. Thank you so much for being on the show. And hopefully, I look forward to a second part, hopefully in the near future. Thank you so much.
Okay. Thank you, Ray.